Energy is defined as the ability to do work. It's designated by E, that's the symbol that we use. And then work is the change in energy of a mass. Basically, anything that has the potential to do something has energy. Now, work and energy are scalars, so they're one-dimensional. Positive in the displacement direction along the path and negative in the opposite direction. Work is done when a force moves an object through a distance. So to illustrate this, let's say we have a block on a surface. There's friction on the surface. Well, if somebody is pushing on the block with a force of P, it's going to make the block move this way. So that force P would be doing positive work because it's pushing in the direction of displacement. Now the friction goes against that. So friction does negative work because the friction force is in the opposite direction of displacement. Work is measured in joules or foot-pounds. A joule is a Newton meter because it's a force times a distance, and then the English unit is just foot-pounds. So force times distance. And there are different types of energy. So actually here, you can see work is the integral of the force dotted with the distance. The dot product of two vectors is a scalar. So that's how come work can be a scalar. Now there are different types of energy. Energy can be stored or it can be dissipated. Stored energy is done by conservative forces. Dissipated energy is done by non-conservative. Conservative forces are things like gravity, spring, pushing, all things that add energy into a system. Dissipative forces are like friction, damping, drag, things that sap energy from the system. So the work done by conservative forces is path independent. So that means that if energy is conserved, then the work that it took to get from point A to point B doesn't matter on the path that you took to get there. It just matters on the starting and ending states. Now, dissipative energy is path dependent. This means that the work to get from one state to another state does depend on the path that you take. So, an example for path independent storing energy. So if you say drop a ball from a certain height, then the ball is going to hit the ground. You could have started with the ball on the ground, thrown it up in the air, and then it lands back on the ground, and it will be moving at a certain speed right before it hits. Or you could have gone to that peak height and then just dropped the ball, and it would still be moving at that exact same speed as in the first case is when it hit the ground. So that's a path independent example. A path dependent example is basically if you are pushing an object on a ground with friction, if you go straight from point A to point B, it takes less work than if you went in a big circle and got from point A to point B by a really long route. It's a lot harder to push something when there's a force fighting against you. So that is a path dependent. Now, energy can be stored as potential or kinetic. So kinetic energy, we abbreviate KE. Potential energy, we abbreviate PE. So if energy is stored, it can be stored in a mass, that's kinetic. So in a moving object like this. And then potential energy would be stored gravity. So if you raise something to a certain height, or a spring, you cock a spring, that'll store energy. Now, energy can be dissipated through friction, non-conservative work. So that would be like friction, drag, damping. Damping is like friction that's proportional to velocity. So one way to think about this is like in hydraulics, you can get damping, and also like a slow closed door. Like when you push harder to try and make it close faster, then it pushes harder back against you. So that's an example of damping. Now, if we look at how do you actually apply these principles? So since work equals the change in energy, then the work from state 1 to state 2 equals the energy at state 2 minus the energy at state 1. So if we rearrange this, energy at state 1 plus work from 1 to 2 equals the energy at state 2. So if an object has a certain amount of energy, you put work into it, then it has more energy at the end. Similarly, if it has a certain amount of energy and you took some energy away, like through friction or something, then it will have smaller energy at state 2. So we can write this out as kinetic energy at state 1 plus potential energy at state 1 plus the work from 1 to 2 equals kinetic energy 2 plus potential energy at 2. Conservative work is positive, non-conservative work is negative. So just like in this example up here above, then the work done by force P was positive and the work done by friction was negative. In the absence of work, then energy is conserved. So in that case, then kinetic energy at 1 plus potential energy at 1 equals kinetic energy at 2 plus potential energy at 2. So when you're working problems, then basically you identify kinetic energy, potential energy, and work at each state, and then plug the formulas in. So next we'll look at what those formulas actually are. Well, potential energy, as we said, can be stored in gravity and in a spring. Potential energy due to gravity equals mass times gravity times height. And this is going to be positive or negative depending on if you are above or below your coordinate frame. Then in a spring, that formula is 1/2 K times S squared, where S is the distance that the spring stretches. And this is always positive. So whether you compress the spring or stretch the spring, it doesn't matter, it's still storing energy. Now, kinetic energy also has two types. There is translation. So kinetic energy of translation is 1/2 mv squared. M is mass, v is velocity. Or it can be stored in rotation. This is 1/2 I theta dot squared, where I is the moment of inertia. And this is something that comes into account when size and shape does matter. Because if an object is just a particle, then it can't really be rotating because it's just a dot. But if it actually has a shape, that's when you would include rotational kinetic energy. And then theta dot is just the angular velocity. But for a particle, if it did have rotational kinetic energy, an example is like, here's the ball, it's on a string, it's going around in a circle. You say it's rotating around this point. Well, then that energy, we'd know that the moment of inertia for a particle is just mr squared. So that energy would be 1/2 mr squared theta dot squared. But we know that v equals r times theta dot. So this just comes out to be 1/2 mv squared, which is that translational energy anyway.